All right, good evening. This is Craig Double. I'm in the physics class or physics course through Thomas Edison State University. I'm in section Oscar Lima 010, and I'm doing this video. This is part 2 of Lab 4, and I'm doing this for the reason to help hopefully help people keep their sanity. I had a hard time trying to figure out how to calculate the estimated gravitational acceleration. There's actually an equation that they give you in the lab, and if you go to the part before question 3, and I know it's backwards on the screen, but if you look up there, there's an equation for gravitational acceleration. It's actually for time, and it says time equals 2 times pi times the square root of the length over gravitational acceleration. So I thought, well, I'll just rearrange that and then try to determine from the data I took, come up with the gravitational acceleration. Well, it doesn't really work out that way. It was very difficult. Either I don't know how to rearrange it or don't understand it. So I did some more research online, and this equation I'm about to show you here is the one you're going to want to use when you're determining your estimated value of gravitational acceleration for table 1 tach alpha. That's 1 tach alpha right there, if you can see it. Again, I know it's backwards, but here's the equation I used, and I'll tell you it out loud so you can understand it. If it is looking backwards like in a mirror on the screen, it's gravitational acceleration equals 4 times pi squared times length divided by the cycle period squared. You got to make sure you square the bottom. All right, that's what worked for me, and I ended up coming out with all my gravitational accelerations came pretty close to what the standard is of 9.81 meters per second squared. That's what your gravitational acceleration is on Earth. So there were some numbers that were, in the 10 and stuff, 10 meters per second squared, but understand it's all meters, and you're trying, if you come out with numbers that are way out of line, then something you didn't do something right, or you didn't do your experiment right, it should all be pretty close to 9.81 or around 9 to 10. Anyways, so that's the equation. Again, it's gravitational acceleration equals 4 times pi squared times the length divided by the cycle period squared. So what is length? The length that they're talking about to use in this equation is the length of the string, and this is a way scaled down version of the actual experiment because I already put it up, but it's the length of the string from the pivot point, so from this point here all the way down to the top of your bob. Okay, so now there's some videos out there you'll see. It'll tell you to take the measurements of from the top of the bob to the bottom of the bob, and the center is your average, and that's your actual overall length. Bottom line in this experiment, to keep it easy, you start out with using 1 meter string. Use 1 meter string because guess what? In your equation, everything's times 1 on the top, so it makes it very easy to come out with a standard number. And then all you have to worry about is punching in, when you're plug and chug, the correct number on the bottom for your cycle period. So now the question is, well, what's a cycle period? So there was some help that our instructor put out there that, and this is this can be a mistake you can make if you don't understand what the cycle period is. The cycle period is, so I'll show you, demonstrate, and I'm not going to let it go until I show you the full cycle. So this is your starting point. If you let go up here, the pendulum will swing, tend to swing this way, and it'll stop here at some point up here, and then it'll come back. That's 1 cycle. So if I let it go, 1 cycle. All right, so 1 cycle is all the way to one side, all the way back to the other. That's 1 cycle. All right, so it's actually not too bad once you know what base equation to use and you understand what cycle period means and what length you're supposed to use. So the only time it'll get maybe a little difficult is when you start going through the experiment later on. You'll start to use different lengths of string, and that's when you'll start to see some things change as far as what you're going to look at or what you're going to determine from the measurements. You'll see some effects and differences in your time period or your cycles. Okay, so let's put this to use so we can kind of make sure we get it here. So I did an example. Gotta find it. All right, so I did an example, and all I did is I took data from my table 1. The first one on the table I used was for the 5-degree mark, and I got, for average cycles, so average of 5 cycles, the time, I got 9.95 seconds. Okay, so you have to divide that. You divide that number by 5, and I get 1.99. Oh, wait, is that correct? Hold on. Divide the average value found by 5. Yep. So when I divided by 5, I got 1.99 for my estimated period. And that's what I use is 1.99 squared on the bottom for my cycle period. So if you take 4 times pi squared times 1 meter, because that's the length of the string I used in the beginning of the experiments, divided by 1.99 squared, I came out with 9.958940431, and that's not too far off from 9.81. So that kind of gave me the when I did it the first time, I was like, okay, this sounds like I'm on the right track. Okay, and I did it for all the. So I went through and did them all, and the numbers I came out with, I'll give you for 10 degrees was the same. For 15 degrees, I got 9.839, and so on. So the highest one I got was 9.8 or 9.95, and the lowest I got was for the, let's see, looks like the 30 degree, which was 9.62. Okay, so you take that number. Once you have that, now that's your estimated gravitational acceleration, or gravitational acceleration, or acceleration due to gravity. All right, so you take that number. Now the next part of this is they want you to determine the percent error. Okay, so there's an equation for that. It is in the physics lab book for percent error, and for this situation, we're dealing with gravity. So everybody understands, or you should understand at this point, that gravitational acceleration on Earth is 9.81. So that's your g, and this equation. So this equation here is just an example of how to calculate the percent error. So percent error just equals. And you want to do this in the top portion first would be gravitational acceleration. That'd be the 9.81 minus your estimated gravitational acceleration. So you plug each one of the numbers you got for each degrees or for each trial, or correction, for each run at the different degrees. So 5, 10, 15, 20, 25, 30. You'll punch that in each time you do the math, and you'll come up with your percent error for each situation. And then all those, so you take gravitational acceleration minus your estimated gravitational acceleration that you calculated for with the first equation, and you multiply it by 100. You take that number and you divide it all by gravitational acceleration again, so 9.81. So just to put that to use, in my first one where I talked about the 5-degree angle, where I came up with a estimated gravitational acceleration of 9.95, 8940431. I took that, plugged and chugged in the percent error equation, and I came out with 1.52%. So it's actually not too bad. Once you understand what equations you use, and then just you kind of think in your mind, okay, does that make sense when you get the numbers? It's not too hard. So hopefully that helps. And the real reason why I did this is because we did have a couple guys and or classmates had a little bit of a struggle with it. So hopefully that helps clear it up. And it seemed to work out after I was done with my full experiment. It seemed like I came out with what I thought was the right answers. Have a good evening.